Hello, I'm Kyle, and welcome to my fall update presentation for my MCDS Capstone project. The topic of my capstone is just-in-time compilation for user-defined functions in database management systems. So I'll begin this presentation with a brief recap of the domain and the problem space in which I'm working. In database systems, we typically express queries in terms of structured query language, SQL. SQL has been around for a very long time, and there are many good reasons for this. It's an extraordinarily powerful language for expressing database queries, but it's not without its limitations, two of which are that it's difficult to modularize and compose, and the fact that it's often difficult to express more complicated application logic in SQL's high-level declarative syntax. Many database systems overcome some of these limitations by offering procedural extensions to SQL that allow users to express user-defined functions in terms of a more familiar programming paradigm. So on the left of this slide, you see an example of a user-defined function expressed in PL SQL, and on the right, an example invocation of this function. So this allows programmers and organizations to use SQL query logic over time and also express these queries in a more familiar style. The problem, though, is that these user-defined functions and procedural extensions to SQL often come with massive performance overhead. One example of the overhead imposed by user-defined functions and procedural extensions to SQL was presented by Ramachandra and others in their work from 2019. They introduced user-defined functions into the well-known TPCH benchmark by re-implementing some of the query logic in terms of UDFs. By making this small change, they observed that the query runtime for some of these analytical queries increased by many orders of magnitude, sometimes up to 10,000 times the original runtime. They observed that the root cause of this performance degradation is a fundamental impedance mismatch between the imperative execution of the PL SQL engine and the declarative execution of the underlying SQL engine. And the context switching between these two modes of operation causes the performance degradation that we observe. This brings us to the goal of my capstone. I aim to evaluate techniques for improving the runtime performance of user-defined functions in database systems. There are two high-level components to achieving this goal. The first is that I develop a novel approach to UDF execution that leverages existing techniques for code generation and query compilation. And the second is that I evaluate this new approach to UDF optimization to existing state-of-the-art approaches. Currently, state-of-the-art approaches to UDF optimization rely on a technique called UDF inlining. There are several requirements implied by this goal. The first is a system with a mature infrastructure for code generation and native query compilation. This is an engineering effort that is well outside the scope of a year-long course like this one. The second is we require a system that integrates UDF compilation and execution with this code generation infrastructure. And finally, we require a system that supports the various SQL constructs that will be produced by the systems that implement UDF inlining. To meet all of these requirements, we perform our evaluation in the context of the Noise Page Research Database Management System, a system developed here at CMU by the Carnegie Mellon Database Group. Next, I'll review the progress that I made on this project thus far. At the conclusion of the spring semester, I completed a minimum viable implementation of just-in-time compilation for user-defined functions in the Noise Page DBMS. This consisted of almost entirely engineering effort that essentially involved the construction of a compiler front-end that translates from the Postgres-compatible version of PL SQL to the internal domain-specific language utilized by Noise Page. In this minimum viable implementation, we were able to perform code generation and compilation for simple UDFs like the one that you see on the left, but we were missing support for several important PL SQL language constructs that will be necessary for the performance evaluation that we intend to conduct. On this slide, we see a very high-level overview of the architecture for UDF JIT compilation in Noise Page. The process proceeds in roughly two phases. First, when a function is defined, we compile the PL SQL to the internal bytecode representation used by Noise Page and store the resulting abstract syntax tree in the database catalog. Next, when the function is invoked by referencing it in a SQL query, we clone the abstract syntax tree that was previously compiled into the bytecode program for the calling query. This resulting unified AST is then fed through the noise page execution engine and JIT compiled. This summer, I had the opportunity to continue work on my capstone by pursuing a research internship with the Carnegie Mellon Database Group. During this time, I made progress towards completing my capstone on several fronts. One of these was the implementation of common table expressions in the noise page database management system. Common table expressions are a very popular SQL construct, and importantly, they are used heavily by the systems that implement UDF inlining to implement iterative and recursive control flow in the SQL language. So we will require support for common table expressions in order to perform our evaluation. As you can see from the bottom of this slide, these are some examples of the types of CTEs that we support now in NoisePage. These include regular or vanilla CTEs, recursive common table expressions, as well as iterative or properly tail recursive common table expressions. Another subproject that I worked on this summer was revising the implementation of several aspects of user-defined functions in NoisePage. The most important aspect of this was adding support for several language constructs that we will require for our evaluation, namely embedded SQL queries and iterative control flow over the results of these queries. The key component of this implementation was adding support for lambda expressions and closures to NoisePage's domain-specific language. We use closures in order to bridge the gap between imperative and declarative execution. Closures are what allow us to push logic down from the PL SQL engine into the regular SQL query engine, and further materialize the results of SQL queries back up into the PL SQL function. In addition, there were several non-engineering aspects of my research internship this summer. I began meeting regularly with several external groups that are conducting related research. This include Dennis Hearn and Torsten Grust from the University of Tübingen in Germany, and Kartik Ramachandra and Surabhi Gupta from Microsoft Research. We made tentative plans to co-author a paper that will hopefully be completed by the end of this semester. Next, I completed a survey of the user-defined functions in the SQL proc bench benchmark. This was the result of research from Microsoft Research that was recently completed. I performed feature extraction and a comparison with a prior survey by Tanuj Nayak and identified the representative functions of interest for our evaluation. Next, I began working on a National Science Foundation proposal for continued research on procedural extensions of SQL in code generation engines. And finally, I conducted a more thorough literature review than I had completed in the fall semester. This included approximately 60 papers, and I really expanded the focus beyond simply user-defined functions to include a broader view of the space of approaches to code generation for analytics. Finally, we arrive at my plan for the fall semester. At this point in my capstone, most of the engineering effort is behind me. What's left is to perform the experimental evaluation of UDF execution strategies. There will be 3 different methods for UDF execution that I will include in this evaluation. The first is JIT compilation through code generation, the technique that I've explored in my work, as well as 2 external sources that implement UDF inlining. The first being Microsoft SQL Server's Freud framework, and the second being the Opfel framework out of the University of Tübingen in Germany. With these results in hand, we should be able to complete the evaluation paper that we began this summer. Finally, I have tentative plans to continue working on a survey paper for code generation techniques for compiling query engines, but this is somewhat orthogonal to the evaluation paper. Here are some further details regarding the experimental evaluation that I intend to conduct this semester. The question I intend to answer is, which optimization technique for UDF execution yields the best performance and under what conditions? The data that we will use for this evaluation will be drawn from the SQL proc bench benchmark. This is a recent work from 2021 from Microsoft Research that synthetically generates user-defined functions based on a massive survey of production workloads. We will select 5 representative functions from this set for evaluation because of the overhead required for each function that we intend to evaluate, which we'll talk about further below. The metrics that we will use for our evaluation will consist of query latency, the most important metric, followed by resource consumption, which may include memory and CPU utilization, and finally compilation latency. The procedure that we will follow for the evaluation will proceed roughly as follows. First, for our technique, the technique that I've proposed, we'll be able to execute JIT compiled UDFs directly on noise page. Executing the inline queries from Freud will require additional preparation steps, which will include getting the optimized and inline plan from SQL Server using the explain command. We will then manually construct the TPL program that implements this plan and then execute this program on noise page. Opvel, like Freud, will also require additional preparation steps. For Opvel, we will have to run the function through the Opvel compiler, retrieve the optimized plan from Postgres, and then manually construct the TPL program that implements this Postgres query plan and then subsequently execute this program on noise page. For this reason, because of all the manual construction of programs that we will have to do, this is why we limit our survey, our evaluation to only 5 representative functions. Here are the primary references I utilized throughout this presentation. Thank you for your time.